Welcome everyone to the AI for Net Zero webinar series. Today, I am pleased to be joined by our guest speaker, Professor Lei Xin from University of Surrey. As everyone might know, the AI for Net Zero webinar series is designed to bring together experts and innovators from both the artificial intelligence and sustainability domains. Our overarching goal is to accelerate progress toward net zero targets, and the series aims to engage and inform communities about research and development at the intersection of AI and sustainability. We will delve into diverse applications across various domains crucial to achieving net zero objectives, including energy, transport, environment, agriculture, and food system, and other applications as well, so and beyond. Today, we are pleased to have Professor Xing, who is based at the University of Surrey. He received his PhD from Newcastle University and then worked as a postdoctoral research associate at Oxford University, Purdue in the US, and the University of Birmingham. He's currently a lecturer at the University of Surrey with a research background in circular economy and especially for chemical and engineering industries. He focused on achieving sustainable growth in chemical and energy sectors through industrial decarbonization and AI-enabled modeling and optimization. He carried out in-depth studies in low-carbon processes and systems, aiming for net zero carbon emission. And he serves on editorial boards for a number of journals, including Energy and AI, CCST, and a guest editor for several other journals. His research project is funded by UKRI, mainly EPSRC, EU Horizon, and the Royal Society, and other international funding bodies. Today, he will deliver a talk on AI-enabled hybrid modeling approaches for circular chemical economy. And without further delay, please join me in welcoming Professor Xing. And may I ask you to, Professor Xing, the floor is yours, but first, could you maximize your presentations slides?
Yeah. Is that okay for you? Can you see my screen now?
Yeah, I will add it. Can you press maximize then? And now we see full. And just if you can hide the bar, perfect. The floor is yours. Welcome.
Okay, so I just maybe use a kind of a laser. Okay, thank you, Ahmed, to introduce me and also give me this opportunity to share our research, focus on the circular chemical economy. So I will give a simple, maybe about half an hour to 40 minutes talk about AI-enabled hybrid modeling approaches for circular chemical economy. So the first question is always that why circular economy is very important. So I use the kind of data. The one on the left screen, left side of the screen is the plastic. The number showing that every year, right? How many waste plastic we generate, and on the other side is a kind of a greenhouse gas. Two type of the green gas house, CO2 and methane. So from these two images, you can see that even the plastic and the greenhouse gas, especially CO2 emission, getting higher and higher every year. So if we don't better use this waste, that will cause a lot of climate problems. So that is why we need to change the growth mode from the linear growth to kind of a circular approach. So to address the circular economy in the UK, right? So we already have established 5 different centers focusing on different aspects of the waste materials. The one I would like to emphasize is here is the Center for Circular Chemical Economy. what we are doing is that we use different approaches, especially the biological route, economical route, and the chemical recycling route to recycle the CO2. This is a very typical greenhouse gas, right? So change to convert that to back to kind of value-added chemicals. So this center was really successful. Several, leading universities in UK joined this program, and we have three different themes from the fundamental technologies to process and system integration, and towards the policy, social and finance aspect. So this project was successfully completed at the end of March this year. So we also have a kind of report can be downloaded from this website. If you are interested, please go to this link and download. So what we are doing at Survey is that we within kind of a scope, we call it circular chemical economy. We do research on two categories. This is only my research. We have other colleagues working on different aspects. For me, is fuel cell and hydrogen production is one, and the other one is CO2 capture and utilization. So in fuel cell and hydrogen production, because my PhD was the protein exchange membrane, a low temperature fuel cell that is using hydrogen to generate electricity. So based on this, I also did some work on the protein exchange membrane based electrolyzer that is a kind of opposite process to split water to generate a green hydrogen. And I also did some work on the high temperature fuel cells like the solid oxide fuel cell and the electrolyzer. So in recent years, I switched my research towards the CO2 capture and utilization. The first one is called Enhanced Weathering-Based CO2 Capture. That project was funded by NERC, and that project was in Oxford. So I worked as a postdoc for this project for 3 years. And because my background is electrochemical engineering, so we also paid a lot of attention on how to use electrochemical route to convert CO2. So we did digital twin, multi-variable, multi-objective optimization. They are all data-driven approaches, and also, in addition to the technical part, we also did kind of economic analysis and life cycle assessment to track the carbon footprint. So the key maybe I call it maybe the core technology underlying is that we needed to develop a physics-based model first and use a model after validation to generate the data, so that we have the data to train kind of a machine learning model, so that we can conduct the multi criteria assessment. So why AI is important, we all know that. So AI is everywhere in our life. So AI also important in research because these two outstanding scientists, right? They they won the last year Nobel Prize. You can see that from their introduction, that the both of them use a lot of machine learning and an artificial network in their own research. And from the publication aspect, you can see AI is getting more and more popular in research publications, even in the highly visible journals like Nature and Science, and more work related to AI have been published every year. So I would like to use this figure to briefly introduce different AI technologies. So when we talk about AI, normally, we talk about the machine learning. That is only one AI approach. And within the machine learning, we know that machine learning is quite important. And within that, that is a kind of a small category called deep learning. And the other part, like every day we use, I believe everyone use ChatGPT, right? And DeepSeek, things like that. So that is a different type of AI, because that approach is based on the natural language processing that is different from the machine learning and the deep learning. So I think different people have different understanding of AI. This figure is only my personal understanding of AI. So in general, why do we need AI? Is we would like to know, if we have multiple variables, if we change the value of the variables, we want to know what's the consequence if we change the variables. So we call it objectives. So the AI, most AI are based on black box theory, that right? So we don't need to understand the physics underlying, but we use AI approach that kind of based on maybe statistics, data-driven approaches. So we can directly build the link between the variables and objectives. So in recent years, so the explainable AI, we call it XAI, is getting more and more popular. So in next slide, I will briefly introduce the explainable AI, because we also did some work in this area. The first approach, we called it the post hoc explanation method. For example, the very popular one is the sharp, lime, uh, because that is a kind of a post explanation. That means we don't know the fundamentals in the neural network, but when once we have the data, we can do something to analyze what's the relationship between the effect of different variables on the results. So, for example, the figure on the right here is a kind of the sharp result. We have the sharp value, can be negative and positive. If they on the left side, they are different parameters. For example, in this case, we have seven, 8 or 9 different parameters. We want to know how big the effect of if we change one of the parameter, so that we can see if the sharp value distribution is broader. That means the effect of this parameter has a more significant impact on the overall result. So if more data, positive data is on the right side, that means the effect of the parameter will have a kind of a positive result on the a positive effect on the result. Otherwise, the effect will be kind of a negative. I will give some examples later. So because the post hoc explainable method is can only give us kind of a quantitative result, but we also want to know the quantitative. So the intrinsically interpretable method is a kind of a hot area for the research. So in here, the physics-informed neural network is a very common approach. In this approach, we can modify the loss function in the neural network, so that we can change the loss function to satisfy different boundary conditions and initial conditions, so that we will have a kind of intrinsic explanation of the model. Okay, so from the next slide, I will give some examples of my research, talk about how AI enabled technologies can help my research. The first thing is AI enabled approach can accelerate the simulation and the prediction process. So I did a lot of models on the electrochemical engineering. So for example, this some work I've done for fuel cells. I did models from the very small scale. I use LBM, that is on the micro uh, level, and also I did some micro kinetics model, that is for the device level, and also the CFD model to couple the reaction with mass transport and the flow dynamic. And also, once we have the device model, I also integrate this into the system to conduct the techno-economic assessment. These models are really good and very complicated and comprehensive. But the thing is that when we run the model, it takes a very long time. So I gave an example is the fuel cell that is only 25 centimeter square, that is relatively small. But if we perform a kind of CFD model on this, it takes a few days on a kind of really a high performance, PC. That is not a PC cluster, that is kind of a desktop, but really, really powerful. It also takes a few days. So if we want to study all the combinations of different parameters, it will take years to run the model. So this is not feasible, right? So if we use AI, we generate some data to train the AI model, so we can have the result in a few seconds. So why this is how AI can help us. So I developed this approach. We called it the M4 approach. You can see that we have different stages starting from M here, right? So the first stage is called multi-variable input. Second one is we develop a multi-physics model so that we train the machine learning methodology. And the last stage is we can perform the multi-objective optimization. So the thing is that firstly, we need to identify some design variables in our reactors. For example, we can identify temperature, pressure, flow rate, and other parameters as our design variables. Also, maybe the geometry of the dimension of your reactor, right? All of these parameters can be your design variables. So we first have this. Uh, we introduce the values of these variables into the model, and we run the model and validate by experiment. Once we can confirm the accuracy of our multi-physics model is acceptable, so we can generate data to train the machine learning model. So the learning model also need to be validated by the some data. The data can be from the experiment, also can be from the physics-based modeling results, right? We use the coefficient R square and the root mean kind of error, the RMSE, to validate the model. And later on, so we can have the optimal design in response to different objectives. So after this process, we can directly link the design variables and the optimal values of these variables to achieve a given target. So I will give some examples as a case study because this webinar is about net zero. So I will give examples of CO2 capture here. So this project was the one I was postdoc in Oxford University. So that is CO2 capture based on the enhanced weathering. So maybe some people don't know what enhanced weathering is. So if you go to the beach, right, you can see some rocks. The surface is like that, right? That means the enhanced weathering process happens. Even the process is really slow. Uh, that means uh, the dissolution of the alkali rocks can make the solution slightly the weak alkali. So alkali solution can react with CO2 to convert the CO2 into a bicarbonate, so that the atmospheric CO2 can go through the reaction and store in the ocean as the bicarbonate. So through this process, we have 38 gigaton of CO2 every year can store into the ocean, because when the equilibrium achieved, that some gas CO2 will degassed and go back to the atmosphere, so that to finish a kind of loop. So why do we need the chemical reactors? So because enhanced weathering, that process is really slow naturally really slow. So if we can use chemical reactors, we can control the gas, liquid, solid triple phase boundaries, and we can also accelerate mass transfer rate and the reaction rate. So in my last few years, we studied different type of chemical reactors, like the trickle bed reactor, the bubble column reactor, and the slurry reactor. The methodology is like this. So we combine the kinetics with mass transport to develop a kind of reactor scale model, right? So this model will be validated by experiment data. So generate a database. So we can perform some parametric study uh, to test the sensitivity of different parameters, and after that we use the data to train the machine learning surrogate model. After that, we can do some multivariable optimization or multi-objective optimization. So that if we use a GA approach, that is for the single objective but a multivariable. If we use NSGA2, that this approach is suitable for multivariables and multi objectives. So we performed these two so that we can have the optimal value for the design variables. Okay, so first things to validate our physics-based model. So we collaborate University of Cardiff, also Professor Phil Rainforth, his colleague in Harvard Watt. So I'm familiar with him really well because this experiment was conducted when he was in Cardiff University, so that we use model to generate kind of curve, and his group develop this process to generate the data. You can see that our model can be very well validated by fields, experiment data, so that we can trust our model to generate the data for the next step. So we studied two different type of approaches. Or the RSM is a kind of a relative simple approach. The EHF, that's kind of a hybrid approach that is relatively complicated. I will not go to the details of the two approaches. If you are interested, you can go to this journal paper we already published, in 2023. In general, once we validate our data-driven approach, right, we use this type of curve, right? If all the data, the x-axis here is the actual data. For example, that can be the CO2 capture rate, that can be water consumption, that can be energy consumption. These data can be the experiment data, or can be the data obtained from your multi-physics modeling, right? The y-axis, the value here are the values predicted by the machine learning model, right? If all the data are on the line here, the dialect here, that means your model is very accurate. But you can see here for CO2 capture rate prediction, so our machine learning model is quite good. The R square is higher than 0.99, but for the water consumption and energy consumption, the R square is roughly 0.9. Anyway, if the R square is 0.9, that means your model is already very accurate. The most important thing is that we can shorten the computational time from few hours or days to a few seconds. So that is why one aspect AI can help us. So the other one is we can also use AI to help us to do some adaptive optimization. I've also take this CO2 capture as an example. Once we have the CO2 capture through the enhanced weathering as one of the process within an entire system, right? We want to know how to operate this process to always maintain the CO2 capture process in a kind of optimal condition, right? Because if we think about the whole system, right, the CO2 capture will require two things, right? The first one is the availability of CO2 as a kind of reactant, right? The other one is we need the power, in particular the electricity from the renewable energy resources, right? So in this process, we have, for example, we have wind turbine, we have a solar panel, we also have a power, the power plant to generate electricity, right? So in this work, we would like to balance, the how much CO2 we have and how much electricity we can generate, so that we need to match them. So we can see in this figure is that we use some historic data to predict the future. Okay, so the methodology is like this. We develop a model. This is a kind of CO2 capture, right? We need energy. We need flue gas CO2, so that we already develop a dynamic reactor model here, and we can also perform the multi-objective optimization. But as I just mentioned, the renewable energy and the flue gas availability, they are variables, right? So we need to use two AI models to predict them, so that we can integrate the results of these two to the multi-objective optimization, so that we can perform the real-time system optimization. So the first one is we need to validate if our, the data-driven model is good enough or not, right? So here we use a long short-term memory, the LSTM approach, uh, to predict. The first thing is the flue gas CO2 concentration as a function of time. So we take the past 500 hours data, and we can see that the curves are the AI results. Uh, the model is very well, right? Prediction is really accurate. And also here we take the kind of winter by power supply. We also select one of the area in the UK. We take the 500-hour historic data, so that we run the LCM model. We can see the prediction is also good here. So after this validation, uh, we can do the multi-objective optimization, right? We have two objectives. The first one, we would like to maximize the CO2 capture rate, and with other one, we want to reduce the percentage of non-renewable energy in the system. Because in some cases, right, if we have enough CO2, but on that moment we don't have a sufficient green energy, not enough renewable energy, so that in this case we need the energy from the grid. So we believe the energy from the we define the energy from the grid are non-renewable, but in some cases this is not. But here it's like this, right? We have two objectives. Constraints is like that. So once we run the model, right, for a month, continued operation, right, we can increase the CO2 capture rate by 17% roughly. And also, very important thing is that we can reduce the percentage of non-renewable energy. This energy is from the grid. Reduce that by 36%. That is our kind of achievement. So in general, that is kind of matching, right? We want to always operate our process to better use, maybe fully use the CO2 and the electricity generated by the renewable energy resources. Okay, next one is about the techno-economic analysis. That is from a different topic, is the green hydrogen production from the low temperature membrane electrolysis. So the KPI here is we want to know the levelized cost of hydrogen, and that means if we sell the hydrogen, each kg of hydrogen, at which price, so we can balance the profit, make the profit zero, for example. So here we use a different approach. It's called the natural language processing. So that first thing is the student gather hundreds of papers about the PAM-based electrolysis, and he ran the BRT, natural language processing. That's kind of a data mining. So to have the thousands of the data can be used, because the data is really scattered, and he also did some shift, and she removed he removed maybe very irrelevant data, so that make the database like hundreds of good data points. So the workflow is like this. So we from the literature data, we perform the natural language processing, data mining, so that we can predict the trend. But here we also develop the physics-based model here. There are some fundamentals, or maybe uh, governing equations in this process. So we can we can predict the performance, and we can break down to know the economic uh, uh, cost of our electrolyzer. So these two models integrate with machine learning, so we can do to know the current hydrogen cost, and to predict the future hydrogen cost. This is a kind of a simplified, flow the workflow. That is taking historic data. We use a neural network to fit the trend to predict the change in future. So I want to can give a few examples. The one is the iridium loading. Iridium is the key catalyst in water electrolysis. So as you can see that in the last uh, 10, 10 years roughly, right? It's because our work stopped at on 2023, right? In the last 10 years, you can see the iridium loading decrease like this. These are historic data. So we can see that with the development of technology, right, the iridium loading decreases. So that we also use data mining to predict in the next 10 years, or maybe next 7 years, 8 years, what the platinum loading, how much can be reduced, right? So after this, we can see that the iridium loading can decrease from maybe 2023 here, roughly 0.37 to roughly maybe 0.35. It's not a kind of large decrease, but we can use model to predict this. And the other thing is about the performance, is the current density. If we can operate our electrolyzer at a higher current density, that means we can generate hydrogen faster. That is about product yield. So current density is also an important parameter. The same approach, we can see that in the last 10 years, the operating current density increase to roughly 2.5. You can see that kind of linear increase. And we also can predict with the development of technology, the current density in the next few years can reach roughly 3.67 in 2030. That is a much higher increase than the reduce of the iridium loading, right? Okay, so after that, we can predict the laboratory cost of hydrogen. We have a kind of uh, a fast case and lowered case. That is a really optimized case, and the solid line here is a kind of uh, moderated. That is balance the very optimal and non-optimal cases. So we can see that in 2030, the hydrogen cost can reduce from roughly $4 per kg to roughly 1.5 kg in the next few years. This target is called 111 target, that is from the DOE, Department of Energy in the US. They have a very ambitious target to achieve $1 per kg of hydrogen in the next decade. So our model showing that maybe 1.5 or 2 is feasible, but that is quite hard to achieve $1. So we want to know what is the bottleneck of the cost, right? So that we can conduct a kind of breakdown cost analysis. So we can see that in 2023 here, right, the hydrogen cost is about 3.94 dollar per kg. So the electricity, the green electricity, I mean, here it takes 82%. That is the maximum, cost to producing green hydrogen. And we also studied the OPEX, CAPEX. We found that, uh, the electrolyzer component, if we need to replace that at the end of their life, that also takes really, really high percentage of cost. And with the development of the technology, right, we can reduce the hydrogen cost to roughly $1.53 per kg in 2030, and the electricity contribution can be reduced from 82% to 73%. Okay, the last example is we use AI to help us do the life cycle assessment here. Uh, we take a very established approach here is the MEA-based CO2 capture system. So, for example, we have the power plant generates a flue gas that has maybe 15% to 30% of CO2 in the flue gas, and it goes through two columns right here. We use MEA to absorb the CO2 and take that to the desorption column. We regenerate the MEA, send that back to the absorption column, and the CO2 is extracted and concentrated as a pure CO2 maybe, and stored in the ocean, in the pressure tank or somewhere. So we believe this process can, environmental friendly, but is that the case? We have a question mark here, right? So what other environmental impact associated with this process? We want to know this. So first thing is the MEA is a kind of ammonia-based solution, right? People nowadays use the Haber-Bosch process, high temperature, high pressure, and a very high energy consumption. And the ammonia also can, be that because that is quite kind of active materials. If we have a higher temperature, that will have a kind of harmful effect on human, right? So also the high energy to for the regeneration of MEA is also uh, energy intensive, so that maybe we can generate a lot of CO2 in the process, right? So our process, the target is to capture CO2, but if we dig in to analyze this process, we can see that a lot of uh, you know our attempts, here can generate a lot of CO2, so that we want to know the effect. So that we normally what we normally do is that like this. We develop a kind of a system level model for this entire process, and we use a data physics model. We run the model, and we couple the LCA model to have the environmental impact, right? But this process is really time consuming, so that we think about use deep learning models to accelerate this process, and later on we can use a sharp technology to explain the model. So that is kind of explainable AI model. Okay, so we compared two different approaches. I named these indirect approach or direct approach, right? So the for the indirect approach, the first thing is here we run the Aspen model, HYSIS model, right? So we generate the data, we integrate the data into the LCA software so that we can have the result. But the second approach, we call it direct approach, is that we run the Aspen model and the LCA uh, as a whole together, and we generate data to train the machine learning model. So we need to compare these two approaches. Okay, so first thing is we want to see the model validation result. So that is for the direct approach. We also tested the indirect approach, but I don't have time to show the detailed results. But for the validation here, we can see the R square is quite high, higher than 0.9996. That is 996. So that if we use the direct approach, so we can have a very accurate machine learning model first. Okay, so how about the expandability of the model, right? So we tested the two models. This is the model one, the indirect approach, right? So we want to trace back, right? So if we have the environmental impact here, we want to see, first thing is human damage, health damage, ecosystem damage, and resources damage. That is the Y. So we want to say what will affect the Y most significantly. So we use the SHARP technology, right? We can see the CO2 product that is the most important parameter for these three objectives. And we also track back again to say what will affect the CO2 product here. So we found that, we have because we studied 5 parameters, we found that the concentration of the MEA has the most significant impact on the CO2 product. So that if we summarize, we can say if we operate the MEA at concentration, higher concentration here, right? So that will have a positive effect on the CO2 product. That means we can operate our CO2 flow rate at a high flow rate. So we can treat more. We can absorb more CO2, so that more CO2 means negative effect on these kind of damages that can reduce the damage of the health, ecosystem, and resources. So this is a logic, right? So that if we compare the direct approach, right, we only have the result trace back to the operating conditions, right? We have 5 different parameters, right? We can have these figures. You can see that all the red color data is on the left of this central line. That means if we operate the MEA at higher concentration, that will have a negative effect on these three damages. So that higher MEA concentration will achieve lower health, ecosystem, and resources damages. That is inconsistent with the indirect approach. So we save quite a lot of time in modeling. So that is AI can help us. And in our group, we are working on expandable AI for the electrochemical materials, fixed informed neural network for the renewable energy prediction, and other type of AI enabled modeling. So to summarize, here, a lot of work published, before is like this, right? So we have some design variables, and people generate the physics model validated by some data from experiment and from literature, and to train the machine learning model, and to do some, multi-criteria decision making or analysis that can be performance, economics, environment, and social. This work has been done by a lot of people previously, but what's something new we can introduce into the system is that we consider the environmental variables. They can be intermittent renewable energy and intermittent CO2 availability, right? So that we if we can integrate environmental variables into this, we will we can conduct kind of dynamic and adaptive optimization enabled by the model predictive control, so that we will make kind of a live chemical process. That means we have sensor, your AI can analyze and predict the environmental variables, and to make sure your whole system, chemical system, can always be operated as at the optimal condition. So that is the next generation of automation. So we called it AI enabled autonomy. So we already published one paper in energy and AI as a review paper. Okay, that is my presentation. Thank you very much for listening.
Thank you, Lee, for the very interesting talk. I will remove the presentation now, and
Yeah,
you can minimize so
yeah,
you can join us and see us now.
yeah.
Um, are you on the browser version? Yes. Okay.
Mm,
It's lots of interesting parts and bits here
mm,
and there. It's really extensive work. So thank you for this. For the entire presentation. I remind the audience you need to sign into to YouTube before you can post your questions, and it will appear to us here. And in my mind,
mm,
we definitely witnessed a lot of breakthroughs because of AI in supporting various activities, optimization, control, natural language processing combined with LCA analysis and data mining of literature. Do you see that there is an uptake of the industries to all of this interesting research, or is there is a barrier between what's being done and what the either
mm,
industry or policymakers are they taking what's
mm.
academics are producing now?
I think that is a really good question, Ahmad. The thing is that we can uh, prove our approach is can be validated, maybe good enough in a small range, but we can't say our model can answer a big question because our reality is more complicated for the industry and decision makers, right? They need to consider some questions maybe bigger than what we can imagine so that we can prove that our approach has a big potential. But if they want to use our approach to answer their question, maybe they will have a really high risk. I think trusted AI will be a big issue here.
Fair enough. So by then you address that with some ideas of explainable AI.
Mm.
Is that something you are still pursuing? Do you see deficiencies or areas where you can improve that part?
That's the thing is because as I just mentioned, AI approaches. Most of AI approaches are black box. Even they can predict result with a very high accuracy. People will ask a question is, so if the AI is such powerful, why not we can use AI to predict, for example, the stock market, right? So people can know which one they can buy and they can earn money, right? But that is not the reality. So our reality is more complicated than the kind of one of the research questions, right? So explainable AI will be the next stage, I think.
Yeah, and in terms of methodologies which relies on physics informed neural networks and the likes, where physics equations are encoded
Mm.
in terms of the loss function. Um, like you seems to list it as a future area of research for energy predictions. Um, do you think that these are compatible with the current neural network architectures? Like, I'm asking this question specifically because we find it a little bit harder to optimize these neural network with standard optimizers.
Yes, that is a very good question. As currently in my group, so we can easily do the ODE, ordinary, differential equations. But for the partial differential equations, that is really tricky. Some cases are working really well, but some cases not. So especially for my research, because we would like to use kind of a really kind of non-linear equations. They're all PDE equation, PDEs. But to start out, these equations are really, really challenging.
Yeah,
Mm.
and what is it? Is there is any learnable experience you could share with us when do we know that it will fail, or what do we do if it fails? So converge.
I think we need this external support. For example, people from with a mathematics or computer science background. This is why we need to have a kind of interdisciplinary team to 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 sort out a big problem, right?
Fair enough.
Mm,
So as aspects which interests me very much is the area where you are trying to predict in the future, the the cost of something which depends on innovation which will happen between now and 2030.
yeah.
And this is the limit of where what is predictable and what's not predictable. So you just give us example of the stock market. What
Mm,
is predictable component of that signal we see in the stock market versus what's not predictable? We don't know if a natural disaster will happen, or geopolitics will affect the stock market. So when we think of uptake of a technology like hydrogen
mm,
in a scale which is in some sense could be, some people could consider it short, 5 years. Some people would consider it long, because that things are moving too fast right now.
mm,
So what kind of, like, I was surprised to see the bands are not growing significantly with the time. So
mm,
you had a prediction, if I recall the curve, was there's a decline, but
mm,
then I would expect usually, or this is what I tell my students when I teach, when you try to predict the future, your uncertainty bands are should to grow larger, because there is the unknown unknowns. And
yes, yes.
so I was surprised that the bands, maybe the scale of the figure was a decline, but
Mhm.
then the range was narrowing.
Yes, so that is a lot of uncertainties here, and the student, have this result. I also, chat with him to how to explain the results. He said, yeah, we take maybe 90% of uncertainty. That is maybe some result we can maybe looks acceptable, but I mean, if we predict, longer future, the uncertainty will be, really, really large, so that maybe the result is kind of that trustable, right? Mm,
Fair enough. I would ask the last question about what is the most exciting piece of work you are looking to work on in the rest of this summer.
Uh, yeah, here is, you know, I will go to Belgium for the Escape conference. That is, something in this summer I'm looking forward to share. And also, in this October, I'm also going to the US for the ICGE conference. That is the most important chemical engineering conference there. So that I'm taking this chance to visit a few universities in the US, because I know some collaborators there. They are working on the PIN, fixed informed neural network. So I'm thinking to take this opportunity to further, expand my, the boundary. So I would like to learn from them and work with them together. Yeah, that is something really exciting.
Very, very good. Thank you for sharing this with us, along with all the exciting work you have done. And I am sure that our audience who are watching us now or will be watching us in the next few weeks on YouTube
Mm,
will very appreciate your talk. Thanks again, Professor Zing, for sharing with us your work on AI-enabled modeling for circular economy, and how it is contributes circular chemical economy,
mm.
and how it contributes to the global effort, and mostly for UK efforts to achieve net zero. With this, we conclude today's session, and I would like to remind our audience that we now hold these seminar series on a monthly basis on the first Tuesday of each month at 2 p.m. British summer time currently, or it will be when it shifts, it's 2 p.m. And for confirmation of the next speaker, please watch what we post on LinkedIn or on YouTube for the next speaker. Thanks again, Professor Xing, and all the audience who are joining us now. And we hope to see you next month.
Okay, thank you. Bye. Bye.